So what I'm going to be talking about today is, it's rather broader than the laser plasma accelerators that was advertised. The reason for that is that there's a very strong tendency for people to actually get siloed into certain areas, and they forget what's going on outside their own subject matter. So what I've done is I've coupled a number of things together to go through the physics of plasma accelerators rather than just laser plasma accelerators. But I'll show you the connection between the other branches of plasma accelerators, like electron plasma accelerators, Wakefield, electron beam Wakefield accelerators, the ion beam Wakefield accelerators, and other things as well. So we shouldn't lose sight that there are other plasma accelerators out there, and they're trying to solve the same problems as the laser plasma community is trying to solve as well. So what I'm trying to do is give you a broad brush flavor of actually what's going on. And before I start, there are two people I would like to thank, actually. And the two people, there's one of them you all know very well. His name is Chan Joshi. He's going to be giving a lecture here, I believe, next week. I think it's going to be Skyped over. The other you may not know so well, and that is Bakar Dangar. Now, those two people are more or less the reason why a lot of us are here, actually, because they started the field of plasma accelerators, or laser plasma accelerators, way back in the early days, and I'll talk about them as we go through the lecture. But both Chan Joshi and Bakar Dangar were really the forefathers of this subject. And there came a time, and it was a precipitous time, when most people in the world were beginning to lose faith in the work that was going on and beginning to drop out. But those two researchers continued, and of course, they found tremendous results, and you'll see that in a few minutes. And those results went on to spawn a huge industry now, and it's one of the fastest growing areas of plasma physics. And in fact, it's the jewel in the crown of plasma physics, because if you look at tokamak physics, they're doing well, but they haven't really achieved the fusion goal yet. If you look at laser fusion, yes, the same thing. They're doing extremely well, but they still haven't produced the goods yet. Now, when you come to laser plasma accelerators or plasma accelerators, we've really actually developed some really useful things already. And some of the speakers this week, in fact, Zulfikar Najmuddin up at the back there, he's going to be talking about some of these ideas and some of the things. And I see probably Dino there. Dino's got some ideas as well you're going to find extremely useful and extremely fruitful. And that's where you can couple now, say, science in with industry, in with applications for medicine and lots of other things. So I'm going to really start right at the beginning of this talk, and initially with laser plasma accelerators. I'll then go on to electron positron beam-induced plasma Wakefield accelerators, and then ion beam-induced plasma Wakefield accelerators. These are all big experiments that a lot of you know about. I'll go on to laser ion acceleration as a separate topic in its own right. Now, we all know that the reason we're here is because you can produce extremely large accelerating gradients from 1 to 100, say, gigavolts per meter for an accelerating gradient. And that is just 1,000 times greater than you would find at, say, a site like CERN, where the LHC is needing something like 27 kilometers of accelerator to get the energies up to the value that is required to do good particle physics. But with a plasma accelerator, you're already getting up to GeV in, say, a meter of plasma, and we'll show that the laser plasma experiments are now several GeV over, say, centimeter scales, which is just incredible. Again, 1,000 times greater than what you can provide in a conventional accelerator. The transient devices, they last for a few picoseconds, and that means that you can continuously use the same medium over and over again, because the relaxation time is very fast, so you can have a high rep rate system. These are just, some of them are just coming online, and we'll hear about that this week, some of the very innovative work that's going on. I'll mention during this lecture to produce very high rep rate systems, so you can have a continuous flow of high-quality beams coming out. They're very small. They're say, the structures that are accelerating the particles are extremely small in comparison to what you'd expect in a conventional accelerator. So I can't go too far talking about acceleration without mentioning these three gentlemen here. One is Landau, of course. Landau produced his famous paper, Landau damping, 1946. That paper, it was rather interesting that didn't really catch on until after John Dawson explained the physical meaning of Landau damping. I guess Landau was probably too bored to go in and explain what Landau damping really meant. He left it as an exercise for the scientists to figure that out. But between, say, 1946 and 1951, there was this interesting period when people didn't really believe in Landau damping. A lot of people thought, well, it's just a mathematical artifact. It's just mathematics. There's no physics behind it. And it was not until about the paper that John Dawson produced in 1961, just dropped off the end there. I don't know why it dropped off the end. 1961, he actually showed the physical origin of Landau damping. And of course, he then went on to be the originator of plasma Wakefield accelerators, both beam-like, there's a particle beam-like, or a laser-type beam. And of course, you can't really mention acceleration without talking about Enrico Fermi. And that paper came out, his paper came out in 1949, about 3 years after Landau's paper. So it's kind of interesting sort of mix there. I wonder if Fermi actually knew about Landau's paper and really understood it before he came out with his understanding of particle acceleration of very high energy particles. So I'll come back to this gentleman later on, John Dawson. Professor Kaw in the front row did work with him when he was at Princeton, and he interacted with him throughout John's life, actually. So a few of us here knew him very well, and we did gain a lot from being associated with him, actually, and collaborating with him. So this is the paper that really spurned the scientific community into getting into this field, actually. Laser Electron Accelerator, it was 1979, which is quite a long time ago, before a lot of you were probably born, actually. So it is a remarkable piece of work, this. It really went beyond the bounds of what was feasible in those days and produced a paper that said that you could produce say, a GeV electron energy particle in about a centimeter. This was just quite phenomenal, actually, for someone in 1979 to come up and say that in a plasma. There were many, many people who would write a paper after that saying, that's not possible, great idea, there's lots of reasons why it won't work. And you can go back into the archives and you can actually then find papers written by quite eminent scientists who could show that the ideas that were put down in this paper did not work. But one of the good things that we had in the field was this guy called Chan Joshi and then Bugger Dangor, because they believed in the idea and they stuck with it, and they actually went on to produce some very interesting and pioneering work in the field. This is a picture you often see, actually. There's different types of pictures. You either get a surfer, et cetera, et cetera. But I thought I'd put this one up because I was recently in Australia, and I tried wakeboarding, and it really does work, actually. If you're actually going behind a very powerful motorboat, you've all seen people who are actually water skiing. They're holding on to the motorboat with a piece of string. And wakeboarding is something that you do with the boat and the wake that is left behind. You actually initially get up in the wake with the string that's pulling you, then you leave it go. And you actually ride the wave behind the boat. And you can go for many, many, if you're very good. I was not very good. I would fall over after a few seconds. But you could actually, the experts could go for quite a long way, you know, kilometers actually, quite easily. So it really is riding the wake of a structure. And if we'll get time at the end, I'll come back and talk about the ideas. You mentioned, Rajesh mentioned the talk you're going to have on the 17th, the talk on space research. the space scientists in the 50s and 60s, particularly in say, Russia, were very, very concerned with Wakefields, but not Wakefields in boats and not Wakefields in laser plasmas, but Wakefields in the ionosphere or in the magnetosphere, where they would actually draw energy from the satellites itself. In other words, they slow the satellite down. And a lot of people were calculating plasma waves, which were just the ordinary, say, alpha waves, et cetera, et cetera. So there's been a long history of people calculating wakes behind objects. So I put this up because this is a very important slide. This sort of sets the historical precedent for what we're doing just now. So in the 1970s, about 9 years before John was actually talking about laser Wakefield accelerators, you had mode locked lasers, and they were only going up to about 1 gigawatt in energy. Sorry, do I go back? Yeah. When you go to, say, the 1980s, round about this point, you're now getting close to a point where you're getting to about 1 terawatt, which that was possible to get some kind of excited beam out, but it really wasn't enough. And at that time, it fixed the idea, because the original Wakefield idea that was put down in John's paper, he had 2 ideas in that paper. One was the laser Wakefield accelerator. We'll describe that in a second. That was not possible using this particular laser configuration. The pulses were far too long. In fact, you have to have pulses that are about half the wavelength of the plasma wave before you can actually start exciting a true wake through the Wakefield process. So when the 80s and 90s started, when those people started the 80s and 90s to do this work, what you found was that they were given these big, long pulse lasers. They couldn't do very much with it. So they started looking at things like the Wakefield and, the beat wave and the self-modulated Wakefield process. And this is where we almost came to an end, actually. Up until about this time here, there was a lot of countries involved. The French were involved, the Italians were involved, the British were involved, and the Americans were involved. Quite a lot of American groups, actually. And one by one, they all fell out. They all dropped the idea, thinking, well, it won't work, it's too difficult, et cetera, et cetera. There was lots of reasons for that, and I'll describe those just later. And so it left two groups really operating. And the 2 groups that were operating this program was the UCLA group under Chan Joshi, and the gentleman I mentioned earlier, Bakar Dangor at Imperial College. So those were the 2 groups that really left in the 1990s. Everybody else had more or less given up on the idea, thinking it will never work. Shortly after that, thank you. Shortly after that, 1986, this is where an interesting set of occurrences happened. Donna Strickland was working with Gerard Moreau, and she was looking at a way of amplifying laser beams. And it was, she was looking at how to amplify radar. The radar people had already developed that process since the war. And it was well known in the 60s that radar people would use chirp pulse amplification. So Donna Strickland, who was a student working for Gerard Moreau, was actually proposing that this actually be a technique for developing a way of amplifying laser beams. And I was at her seminar. I was at Rochester at the time when she was there. And there's a publication where she actually has the drawing of the radar chirp pulse amplification experiment together with her laser plasma amplification, her laser chirp pulse amplification experiment as well. So they're almost identical, actually. And that was in the early 1980s. She published, I think, the paper in 86. And it took about a few years for everybody to... So it took a number of years for someone to do something. And of course, now we're at this point here. And if you want to talk about optical parametric chirp pulse amplification, talk to Rajiv here, because one of the pioneers is in the Rutherford laboratory, or was at the Rutherford laboratory. I think he's retired now, hasn't he? Yeah. So that's where we are now. We're in this regime here. We're going up slowly, but surely perhaps to an exawatt. So maybe we'll get there in the next, say, 10 years. But we're hoping to do something important before then. So these are the three schemes that were outlined in that paper that John Dawson actually wrote. One was the laser Wakefield accelerator, which you probably are working on just now and everybody knows about. The other was the plasma beat wave accelerator. This is where you take two beams, laser beams with this frequency separation equal to the plasma frequency, beat them together in the plasma, and you generate a modulated structure in the electromagnetic profile here, and that generates the blue, which is the electron plasma wave. And then you go for this other one here, which is a self-modulated laser Wakefield accelerator. And this is a relatively long pulse, just one pulse. But what happens is that it relies on an instability to actually start modulating itself, so the pulse breaks up and it modulates itself, and it drives the electron plasma up, which is the blue structure here. So you get the two plasma waves generated. This is the one that's perhaps the most common. Everybody uses it now. But in the 1980s, 1990s, this one just did not exist. We had to wait until the chirp pulse amplification took us up to many, say, tens of petawatts before we could do that, and very, very short pulse. So we're looking at very short pulses rather than intensity or energy. So these two were the ones that people were working on, and they actually provided us a lot of insight because there was a huge amount of work done in the early days. And this is just an example of the amplitude modulation of two laser beams that are separated by, say, the plasma frequency, and you trap electrons within these structures here at the nodes here, and that's due to the ponderomotive force that is pushing away from the regions of high intensity and pushing the electrons into these buckets here. So you end up with electron density bunches that are moving with the phase speed, which is equal to the group speed of the modulated pattern. And if the group speed is close to c, then this beam is moving close to the speed of light. So you can go through these calculations and you can show very easily that you get this parallel electric field, which is proportional to, say, the density of the plasma. So the higher the density, the higher the electric field that's accelerating the particles. And a typical, in the early days, the typical electric field that was accelerating particles was about 10 to the 8 volts per meter, which is quite a large field. And this is just breakdown of the details of what's going on in one of these sort of modulated structures here. You've got a ponderomotive force, which is actually acting away from the region of high intensity there, and it's pushing the electrons into this region. This whole thing is moving at a group speed, which is just less than the speed of light, because you're looking at a plasma that's underdense, where the plasma frequency is less than the laser frequency, is much less than the laser frequency. So this is approaching the speed of light. And these electrons, which are then trapped in there, are moving at very, very high speed. And of course, that's proportion, that force that's pushing them in is the ponderomotive force, which is actually acting on the electrons, pushing them out of regions of high intensity. So that's well known, it's been known for a long time. So the beat wave generation, the equations are very simple. One of the main things that stopped the beat wave from really going places was it saturated quite early on with relativistic nonlinear saturation. So when the oscillatory structure of the Wakefield itself began to increase in amplitude, it introduced a relativistic frequency shift. That frequency shift would then not be in sync with the beat wave. The two laser beams that you come in with are no longer in sync with plasma frequency because it had actually reduced its frequency, and that would produce a saturation effect. And that was known. Rosenbluth had worked that out with C.S. Liu about maybe about 5 or 6 years before that, actually. So these were well-known problems. The other thing is that it would actually go on and perhaps limit the amplitude of the Wakefield to an amplitude that was perhaps not acceptable for really good acceleration. The other problem was that if you've got collinear beams going down through the same plasma, it was very, very difficult to actually have them aligned. And Colin Danson at the Rutherford Laboratory built a double oscillator system of two different types of, say, doped glass. It's still neodymium glass, but two different types of material, yig and yang, and that would produce two frequencies, and they were collinearly And those experiments went on to show, yes, you were producing relativistic plasma waves, but there was very little acceleration. The acceleration that was measured by Chan Joshi, and he used CO2 laser, and CO2 laser has a very large bandwidth, and you can pick out two frequencies from that CO2 laser quite easily and have them beat together in a plasma, and you can produce energies up to about 30 MeV. That was the limit of particle acceleration in the early days. So that was round about the late 80s. The other one I mentioned was the self-modulated laser Wakefield, and what you found there was that you had a relatively long pulse, which was much longer than the half the plasma period that you really required to actually produce the wake. So what you relied on was an instability, and this is a Raman forward scattering type instability, a modulational type instability, which would actually reorganize the original envelope, laser envelope itself, to produce these modulated structures. And again, that modulated structure would act on the electrons and push the electrons in through the ponderomotive force and drive up the Wakefield. This was an experiment that was really done in the lab in the 90s. We still hadn't got to some the really short pulse lasers yet. They were just coming online. So Modena, working with Chan Joshi and the Rutherford people, were looking at this sort of self-modulated laser Wakefield accelerator and getting good results. I mean, they were getting up to hundreds of MeV. And that was a high-energy tail. There's no beam here. This is just a high-energy tail on the electron distribution that's part of a much colder electron distribution function that goes all the way down there. So we're really just talking about pushing electrons out to about 100 or maybe a few hundred MeV. Now, they can be important for some applications, and I think Zulfikar Najmuddin may actually mention some of those applications. And I think, not mistaken, was that your first experiment, Zulfikar? About that. I think that you were there about that time. I remember you working there. So this is the sort of historical introduction. The last thing I'm going to talk about is this short pulse laser. Something's going wrong there. But it's short pulse Wakefield generation. And what we've got here is, if you look back at this structure here, if you've got a series of pulses, if you could actually produce a series of pulses like that, you would automatically drive up the structure here, which is the electron plasma wave, which is in green. So the plasma wave would naturally be pumped by a sequence of short pulses, and these were all produced at about, say, a wavelength, or the pulse length was about half a plasma period. This here is the intensity of the laser. Intensity. Yes, E squared, yes. So if it was the laser pulse, it would be oscillating back up and down. It would go below zero. And of course, what you find here, this is just E squared, the intensity of the laser. So if I take that idea, this is one pulse going in. These are old calculations that we did way back in the 90s, so you can still see that we're using some old computer graphics and things like that. But they didn't really matter. What you could do is you could take one pulse, short pulse, you generate a train of plasma waves. You take two pulses. The first one generates a train, and put the next one in. You generate another. You pump it even higher. You put another one in, pump it even higher. This is an idea that's been picked up recently because people now are building very, very sophisticated fiber lasers, where the fiber laser would be, say, producing a pulse of that shape there. Very high rep rate, so you can actually stack them together and then drive up a plasma wake that way. And the group at Oxford under Simon Hooker are doing just that. They've got a program to build up a series of fiber stacked pulses, 1, 2, 3, 4, a number of them, and then have them build up the plasma wake. And you can then have a controllable structure that you're generating, as we'll see that sometimes these beams that you produce are not controllable. So going back to the problems that we had with the, say, self-modulated laser Wakefield. This is a sort of typical pulse shape going in, and this is the plasma wave that you would produce. And eventually, turbulence would get you. Before that, the plasma wave that you're trying to use to accelerate the particles broke up. And this was an experiment that the French did. And I think that decided, well, it made them decide not to pursue the program. They pulled out about that time because that it was a showstopper, and they didn't think they could go any further with that. So they did that, they pulled out. But this is, again, sort of a forced plasma Wakefield where the plasma is not too long. The laser is not too long, i.e. it's a number of plasma wavelengths, but it's not too short for it to be a true Wakefield. And this was Victor Malker stuff. We're getting close to a magic date. We're around about 2002 here. And of course, you again get these very high energy electron tails being pulled out. There's still nothing of really interest to people who are wanting to produce beams of particles. So these are just very high energy particles that are being pulled out. You get up to about 200. I think probably the record is about 400 MeV. So this is work that was going on, again, just round about the time before Chirp pulse amplification lasers became important. This all changed. So people knew from the paper that John Dawson had published, that if you had a short pulse of anything, a photon beam, electron beam, neutrino beam, ion beam, you name it, you could have a muon beam, you could even a gravity beam actually could probably, a beam of gravity waves could probably do this moving through the plasma as well. So that there's no reason why any of these particles cannot actually generate a Wakefield. So what we've got here is depicting a very simple illustration of what's happening. So we've got a photon, electron positron, a muon, an ion. They're moving close to the speed of light, c, and they're moving in a plasma, and they will generate the plasma wave. And that's the paper that John put together in '79. So you can use those particular particles to drive the plasma wave. Now, I'm not advocating that we use neutrinos that we produce in the laboratory. You have to go to an astrophysical source to get the intensity of the neutrinos high enough to drive a plasma wave. And the intensity that you have to get can only be given by, say, a supernova. So your neutrino experiment can only be found in a supernova. And it's possible that, say, a gravitational wave that's produced in, say, colliding black holes or something, they could actually produce a wake behind them, and that wake could actually drive, accelerate electrons. That's just a suggestion that we could discuss during this meeting, since this is going to be a discussion session at the end of the talks. So these are the equations, so you can show the equations are almost identical. For the electron beam case, this is the simple harmonic oscillator type equation for the plasma wave. It's a cold plasma wave equation. This is the density of the plasma wave. So what we're looking at here is the fluctuation in density round about some mean, and that's the plasma frequency, and that's with time. And this term here is the driver now, so this is the electron beam for the electron beam driver case. That's, again, the plasma frequency. For the photon case, the case that we're going to be looking at with photons, I've written it in a form that's similar to this. Normally, you'd write that in the form of, say, the electric field squared, or the normalized, say, electric field, which we call the quiver velocity squared. But I've written in terms of the number of photons, which is just the energy density, which is E squared divided by H bar over omega. And that's just a way of writing the equation in terms of the number density to show that there's a similarity between that and that. And of course, the neutrino one, I've written down the simplified version of that. This is the equation that you would actually derive for a neutrino beam of density n mu. So you've got a very short neutrino pulse moving through a plasma. GF is the Fermi coupling constant. This is a very, very small number. So this effect is very small unless that number is very, very big. And of course, you would only have to get this from a supernova or something like that. And you can go back to the equations of neutrino physics, or the electroweak coupling, and look at Beta's papers, etc. And you'll find that that equation just drops out naturally from from his formalism. I said that there's identical physics going on in both the, say, the electron Wakefield case and the laser Wakefield case, and this is just an example of what they did from UCLA. They showed you exactly the same wake structures being generated. This is the laser beam moving through a plasma from the bottom left to the top right there, and they did the same simulation with an electron beam moving through the plasma, and you get the same density perturbations, the density structures, which are green here, and these are the bunches of electrons which are producing the very large electric field, which are moving close to the speed of light, or moving it close to the speed of the beam, or the photon beam here, or the electron beam, and they're actually then providing the accelerating gradient for the particles to be accelerated. Everything changed about 2004. There's a remarkable paper, three papers in one journal, Nature. It was a plasma revolution, people call it. What happened was that there were three groups. There was Victor Malka's group, which is at the bottom here. He always sort of gets to the top in most publications, but in fact, this is the correct way the papers were received. Stuart Mangle's paper, which is from IC, Imperial College, was the first paper, then the Cameron Geddes paper, then Jerome Fair's paper was the last to be taken on board, actually. They were all published in the same journal. I don't know where that came from. Oh, right, never done that before. This was the where we actually really got onto the most recent work, where we're using short pulse lasers. The CPA had now been adopted by all the big labs, and now these three groups had produced a result within a few months of each other and published in the same journal. 6 months after this article came out in this journal, this journal was published, there were, I think, 14 groups around the world simultaneously had produced similar results, which is quite remarkable. I mean, that shows you that there's something really happening. And this was the result. This was the monoenergetic beam of electrons. It's a modest, say, 70 MeV, but that was produced by a system of lasers, which was quite modest laser beam, actually. So it wasn't a really intense laser beam that was producing that. And that was done at the Rutherford and producing a very well-collimated beam, and it was about an energy spread of about 6% in those days. So it's very, very, very good quality beam for things. And the LBL people were working with the Oxford group, produced shortly after that about a GeV. So they produced a GeV beam, and then shortly after that, they've got the highest energy, which is just above about 4 GeV. I think a lot of people are between, say, 1 or 2 GeV and about 4 GeV now. So that's the highest energy so far that has been produced by one of these laser plasma accelerators. This is the beam quality here. So it was about that time, everybody decided this is a very important area to get into, and so they started working vigorously, building up lasers, and everybody now, there's almost the whole, except I think probably Africa. I don't think Africa is the one continent that are not involved in this. So we've now gone beyond what is possible using analytical theory. Up until, say, the Wakefield, etc., we could do analytical theory, and it was perfectly okay. What happened was, with this result, there was a gentleman called Sasha Pukov. You may know him, and he had been doing simulations, and he had shown that you needed a much, much higher intensity laser to actually produce the wake structures that we were showing in the laboratory. Now, there's a number of reasons why the simulation said that, or the simulation results indicated that, and there's a number of reasons why the experiment succeeded. So there's a disparity now between the simulations and the experiment. So that's something that we can talk about afterwards. and we can go through some of the details. But it's also to do with photon acceleration. So what's actually happening in the simulation, you initialize the laser beam in the plasma. In the real experiment, laser beam is coming from vacuum. It's coming from some distance away. It's coming through a vacuum pipe. Then it hits the plasma. As it hits the plasma, it actually undergoes severe pulse distortion. And that was also noted in the experiments. So people saw photon deceleration at the front and photon acceleration at the back. So the plasma itself was organizing the pulse into the shape that it required to produce the wake that would then accelerate the particles. So the simulations were not always exactly right, but they were pretty good, actually. And this is one of the examples of the simulations. What you have here is the laser beam going through the plasma, and it's basically quadramotively forcing all the electrons out from its volume. So the electrons are moving rapidly out, and in the frame of the beam, or the laser beam here, these electrons are just being thrown out. But of course, that leaves a very large positive space charge in the center. Of course, they come back in, and they come back round, and they pile up in this region here, and that region there, and that region there, and that region there. And that sets up the electric field for particles to then be accelerated. Now, there's a little bit of luck that was needed there. And again, there's a lot, sometimes you make your own luck. And what happened was that the intensity at this point here, this point, was so high that the plasma electron density was so high that that wave, the plasma wave, would break and release particles into the bubble regime. So those particles were being released into this regime here. So that meant that you had a source of particles that were actually then being forced into this region here. Now, in the wake fields that we actually produced before, you had to use an injector. And in fact, Chan Joshi's group used an old electron beam that was coming from a dentist's X-ray piece of equipment. So they cannibalized an X-ray source that was used by a dentist, took the electron beam out, modified it, and used it to accelerate in their wake fields. Their wake fields were not powerful enough or not large enough in intensity to break. So there was no breaking of the particles that would actually produce a seed or a source of particles. This is the injection problem. The injection problem is still a big problem. People are looking at it seriously to see if they can inject a certain number of particles in the right phase, the right position. So this is the point that we're at just now. We're still investigating, say, injection processes. That's a major area of research that we can talk about during this week. So the design concept for a laser Wakefield accelerator, we haven't really stopped looking ahead. So people are actually looking constantly at what we can be doing. So you've got to have a number of things in place. You've got to match the oscillatory velocity of the particles in the beam, the laser beam, that's A0 with the spot size. You've got to have the right length of plasma so that you're not going to have any pump depletion going on before you outrun the plasma. You've got to have dephasing. The dephasing is when the electron beam that you're accelerating or the particle beam that you're accelerating is actually outrunning the wave itself, and it gets to the point where it's beginning to decelerate because it catches up with the opposite electric field sign and it begins to decelerate and it gives its energy back to the wake field. You've got to have a sufficient energy gain. Obviously, that depends on the power of the laser. You want to have a large enough charge, and again, this goes back to the wave breaking argument. You want to be able to produce enough particles in the, say, wake to actually be accelerated efficiently to high energy, so you've got a high charge that can be useful for a lot of experiments. Efficiency's obviously got to be very important. And then the critical A0 for self-guiding. This is where you've actually self-guided the laser through a long enough channel rather than relying on just the Rayleigh length to provide the length of the channel. And so this was all put together by Wei Lu, who's been doing a lot of simulations with the UCLA group and IST group. He's now back in China. And I've just outlined, say, 3 of the results that he's produced, actually. And this is the petawatt of the laser that would be required. This is the pulse length of the laser. This is the plasma density that you would need. This is the spot size, the length of the plasma. This is the classical VOS over C of the laser beam. This is the percentage of the fluctuations that you can withstand. This is the charge, and this is the electric field, or the energy that you get out at the end. And so if you start off with, say, 100 petawatts, you're getting about a GeV. That's about right. People are getting about a GeV with about 100 petawatts. If you go to 2 petawatts, change the parameters slightly, you're going up to about 10. That's quite a push, actually, because the Bella experiment is around about, say, this mark here, but it's only producing about 4 GeV. And then, again, by changing the parameters, tweaking them again, you can get up to 99. And this is in one path. This is, go to 99, though, you need a plasma that's about 16 meters long. That means that you need self-guiding for 16 meters. That means that you've got to have your plasma uniform over that distance, which is a tall order, and that's a difficult thing to achieve just now. So this is a roadmap of a single-stage 100 GeV accelerator that would be of interest to particle physicists. So I've thrown this in because this is something that Zofika Najmuddin is going to be talking about, and this is some of his work that he's been looking at, and some of the work that, say, Dino Jaroszynski's been doing, and a number of other people around the world have been looking at the Betatron radiation that's coming out of these systems. And when you've got an electron that's actually thrown into the wake structure, it's going in with a momentum which could have a transverse component to it, and that is then going to be moving in a structure which has got a positive charge in the center, and it's going to actually be pushing the electrons in from the outside. So these electrons are oscillating along in this fashion here. So as the electrons are oscillating, they're going at relativistic speeds, so they're generating radiation which is coming out in the forward direction, and that radiation is coming out as X-rays. So you get Betatron X-rays. If the electron beam catches up with the laser pulse here, it can undergo additional, say, acceleration and oscillations, and you can perhaps get higher energy beams coming out, and again, Dino will talk about that. And that's just some raw data that's been taken by Zof. These are the energy of the electrons, and this is an X-ray pulse, and that was published about a year or so ago. So I'll now go back to the electron beam stuff, because I think they're all very much together. You can't separate them out because there are a lot of similarities between the electron beam driven case and the laser driven case. And with the electron beam driven case, we're looking at the similar scenario. You've got to have, say, some kind of drive beam there, and that drive beam is going to be short in comparison. The length of it is going to be short in comparison to the wavelength of the plasma, so it's going to be about half the wavelength. And you have a drive beam, say, in that point there, and this is going to be accelerating due to the electric field that's produced by the Wakefield. So again, this is an idea that was put forward by John Dawson and his group, and there's been a number of successes in that, notably the SLAC experiments under the, say, guidance of Chan Joshin, called the sort of facet series of experiments. And what you found was that Chan Joshi got the SLAC board to give him SLAC Accelerator to actually do experiments on plasmas. And he's talking about plasmas now about 1 meter in length, whereas the laser plasmas, which I just threw up in one of the slides, are usually about 10 centimeters, no more. Some people have got techniques to make it longer or shorter. I didn't tell you the original experiment that was done at the Rutherford was done with a gas jet. And so SLAC is now used routinely for electron beam Wakefield accelerators. And so the energy of the SLAC beam is about 20 to 50 GeV. And you'll hear about this talk by Chan in, I think, next week. So I'll just run through some of the highlights of the talk that he may give. And so we were talking about an intense laser beam. So the power of this laser beam that's actually going into the system is of the same power as, say, the laser beams that are people using. It's about 1 to 5 petawatt class laser system. So it's got the same power going into the plasma. It's directly pushing the electrons not through a ponderomotive type of force, but just by the Coulomb force, and it's evacuating the region round about it with electrons, so you end up with this blowout or bubble regime. It was interesting in the plasma Wakefield accelerator community, the laser community came up with the blowout regime, and the electron beam community came up with the, the laser people came up with the bubble regime, and the electron beam people came up with the blowout regime. So you had this conundrum for quite a while, but now they just rely on, say, just calling it the bubble regime. So this is just depicting what's actually happening. Again, this is your plasma wake that's being generated by this electron beam. You evacuate all the electrons from this region. The electrons, this is moving at close to the speed of light through the plasma, which is this sort of browny color here, and they fall back round, fall into these spots here, creating this high-intensity electric field that's actually accelerating the particles. I'll just go through this quickly. So this is some of his most recent work, and he's going to be talking about accelerating two bunches, and he's been able to do that. The previous experiments had very high-energy particles accelerated, but it was, again, a high-energy tail. He's managed to produce beams that are single beams coming out of this accelerator. I'll quickly go on since I noticed that time is passing. He's also used the positron component of the SLAC beam to use positrons to drive wake fields, and he's shown that you can accelerate wake fields very easily to very high energy. So again, you can gain energy in the wake field that's generated by a positron bunch. So you can actually have either electrons accelerated using the electron wake field accelerator, or you can have the positrons producing accelerating field, which will accelerate positrons. So we've been able to, or he's been able to show that it's a very universal process. This. And as I said earlier, you can use it to accelerate other components, and Raul Trinas has got work that's going on looking at photon acceleration in similar wake fields. So and also, I mentioned earlier, you can do it with neutrinos, etc. So the progress in the beam-driven plasma accelerators, you've done two beams with the electrons, so you can successfully accelerate two beams. You can do the same thing with positron acceleration experiments. You can accelerate the positrons easily with the positron beams. One of the things about the positrons, they're developing this technique of having a hollow beam for the reasons that we're going to after the talk, where you've got particles, the electrons are no longer being pushed out because the positrons are positive, they're being sucked in, and the form or the formation of the wake is slightly different. And so people have been looking at different techniques to produce a better wake in the positron case, similar to the one in the electron beam case. And they're both generating low emittance beams. So that's Chan Josh's stuff. So this is almost coming to the end of the electron and positron accelerators, or the Wakefield accelerators. So there's an experiment you may have heard of at CERN. A number of the people in the audience are part of this. And what they've done is they've dedicated a beam line, which is the SPS, which is a proton beam that feeds into the LHC. It's about 450 GeV beam, and that feeds into the LHC. And what they've been doing there is they've been doing experiments over a fairly long plasma and driving the wake using the positron, the proton beam. Now the proton beam is moving in close to the speed of light. It's moving through the plasma, and you're generating a wake field. The ideal situation would be if the proton beam was half, or the beam pulse width was half the plasma wavelength. That's not the case. It's many, many plasma wavelengths. So they've got to rely on a modulational type instability. So this is the plasma self-modulation of a long beam. This is a proton beam going in. And you can see after a certain time here, it's beginning to modulate. And you can see the plasma wave is also being produced. So you've got the beam being modulated by this it's a transverse modulational type instability, and you're generating this very strong accelerating structure here. I won't go through this. We can show talk about that later since time is pressing. We'll go through the parameters later. But basically, you end up breaking the beam up into beamlets, and each beamlet drives a plasma wave. And so far, they've been able to put the beam through, but they haven't actually accelerated any particles. The ideal scenario would be this case here, where you're actually producing a very, very short pulse. This is the short proton driver. There's a paper that Alan Caldwell produced about 8 years ago, and he was using the very, very short driver here to actually produce a wake. So the pulse length was of the order of the proton pulse length was the order of the plasma, half the plasma wavelength. So that was driving a very, very strong wake, and you were getting these very large accelerating fields coming out. And he was predicting that he would be able to produce TeV beam in about 600 meters with that. Now that's a long plasma, 600 meter of plasma. It's a long plasma. We still haven't got that there yet. So these are the key structures, the key issues for plasma accelerators. We've still got to actually work on the structure issues, the wake excitation for driven drivers. Each driver has a different conditions that you require for the structure, etc. Energy spread is still a major issue, beam loading, pulse shaping, transformer ratios, etc. Stability issues, that's still a major problem. This one here, the injection issues, how are you going to inject? The self-injection, which was the wave breaking issue that I talked about earlier on. That's the wave breaking, controlled injection, shock injection. You've got ionization injection. So you get these problems that we still have to work on and really solve, and a number of the lectures that you'll hear just this week will actually go through some of these issues. And the overall design issues, we know from simulations that you can technically get to very high energy, but can you actually make that feasible as an operating structure? We need high rep rate. One of the things that we really need here is a very high rep rate system. SLAC has a high rep rate system. The lasers are getting there. What you would really want is a kilohertz high rep rate petawatt type laser if you're going to compete with the particle physics community at the moment. That's probably not in the cards for quite a few years to come. I'll finish off with this the ion acceleration models that people have been looking at. And this is where you take a very intense laser beam, hit a target, you get the electrons are pushed forward, come out the other side, and you get this sheath field. This is called the target normal sheath acceleration. So the TNSA, normally called. You can get TeV, teravolt per meter from this. But in fact, it's a very small structure in size, about 5 microns. So the actual energies that you're getting out are not anywhere near TeV. And so you're getting, say, tens of MeV from something like this. So that's the very first ion acceleration scheme that people looked at. You're not talking about, there's no wakes here. What we're talking about is just a laser impacting a solid here and pushing the electrons through the system, coming out the other end and generating a very large sheath field at this point here, accelerating the ions from the back surface here. And this is some experiments that have been done by Dave Neely and his workers actually showing the efficiency is, pretty good. I mean, you're getting up to about 6-7% efficiency. Theoretical limit is about 20%. This is something he gave me. We need about 250 MeV protons for useful medical applications like ion oncology, and a number of people in the UK are working on this at the moment, also in America and also in Europe. And how do you get there? Well, hit it harder generally works. Maybe you need a new laser, try something new, light pressure. So people like Alex Robinson have been looking at light pressure. So what they're taking is a concept. Again, this is going multidisciplinary. This is a concept that you've got for from laser interacting with matter. So the pressure on a structure is given by the intensity divided by the speed of light. That's if the photons are absorbed by the structure. So So that's the light pressure on a structure. And if you're hitting a bit very forward very, very rapidly. This requires a perfect pulse. It also requires, in other words, that you don't want any modulations of the surface because you'll be pushing the surface at different, say, with a different force, and you break up the surface. So you've got to be very careful how you actually organize your laser. This is predicted to have a high efficiency and also a narrow band of energy that's being produced. And this is some simulations that Alec Robinson has done. So with a circularly polarized beam, you're getting a fairly interesting beam up to about 500 MeV here. Of course, remember, this is simulations, and with a linear polarization, you're not getting that. There's interesting differences between these two, and that's all wrapped up in the physics of what's going on with the different structures, either circular or polarized, whether you get a J cross B oscillatory structure that's actually forcing the surface back and forth. So it's predicted that we could probably get to about 250 MeVs, but we're needing intensities, regular intensity of about 10 to the 22 watts per square centimeter, and that's now up at the multi-petawatt, maybe 10 petawatt class laser systems. So laser drive ions, the current situation is that we're getting fairly good quality ion beams. These ion beams can be used also for proton radiography. People can use them for experiments in other areas as well. So we're getting some useful beams coming out that can be used elsewhere. And Gemini at the moment is giving about 30 MeV. So this is what you'd want for the future. So this would be the capability. You'd want to have something at 10 to the 12 ions, about 10 to the 1 to 30 MeV, 10 to the 11 ions, about up to 200, 300 MeV. And that would be requiring a petawatt class Ti-Sapphire laser, which would have reasonably high repetition rate. This is the future now. So we're getting to the future of what of the subject. So the most powerful lasers are being built in 3 countries in Europe under the ELI umbrella. It's the Extreme Light Infrastructure. The centers in Czechoslovakia, Czech Republic, Romania, and Hungary. And these are, they would like to build something like 10 to 200 petawatt lasers. At the moment, they've got petawatt class lasers, and they've got up to, say, 10 hertz or even higher. And the goal is to produce 10 GeV in a single stage. Vulcan 20 petawatt, which is being put forward at the moment, is capable of going up to multiples of 10 GeV in a single hit. It's debatable whether or not that will be a high rep rate system, but with Vulcan at the moment, it's a single shot system, not giving you beams, but it would be a proof of principle for a very high rep rate system. Again, near future, we'll get the center in Munich for building very high power lasers, 3 petawatt, 10 hertz. The Scottish Centre for Particle Accelerators. This is Dino. We'll talk about that. That's online now. I think they're commissioning the laser. That's about 0.35 to 1 petawatt. And that's mostly going to be used for, say, interesting acceleration type physics, X-rays, hadron studies, hadron therapy applications. A real challenge for plasma-based acceleration is we've now been able to show that you can accelerate particles, but can you actually turn that into an accelerator? So we still need a lot of science to be done to actually turn concept into reality in terms of a device that is very useful. The one that's probably as useful as, it's just gone. The one that's probably going to be near term is the Betatron and the X-ray source that we'll hear about this week. And it requires, the field still requires combination of accelerator physicists, plasma, and laser physicists to join forces. And I still think that you need to have a very broad, say, mind to encompass all the processes that are going on. One thing that I should have said earlier on is that when we're looking at, say, the laser photon acceleration process, that was used by Chandrasekhar's archenemy, Eddington a century ago to look at the luminosity mass ratio of stars. So that was an interesting application of photon acceleration that he used. And the future looks bright, and thank you for listening. Thank you.
Thank you very much, Bob. Thank you very much for showing us the exciting research which has already been done and the exciting questions which still remain to be answered. I'm sure he will be happy to answer questions.
Yes.
If lasers can accelerate the particles efficiently, then why we need beam-driven accelerators?
If the lasers do it efficiently, I think there's two reasons for that. One is, A, we've already got the SLAC accelerator there, so it's already a very high-quality beam that you can use to do beam Wakefield studies. The lasers are just getting there. SLAC beam is a high rate system, remember. And I think that if we're looking at the future of, say, particle accelerators like CERN want to look at, they've already got a TeV accelerator. If they're going to look at the next generation or the one after that, they don't want to throw that out.
It is just boosting the energy of the existing Linux?
Boosting the energy, yes, it's like a transformer ratio. You're boosting the energy of the existing beam, yes.
Where are the limitations to get the bubble regime in beam-driven Wakefield accelerators?
The limitations are that you've got to have a high enough charge in short enough bunch length to produce the Wakefield. And you have to go to a plasma that's got a density that would give you the correct accelerating gradient that will give you the acceleration of the particles. And you have to have a dephasing length that is that's long compared with the acceleration process.
Okay, thank you.
One question.
My question is that UCLA people are doing the dielectric accelerator. Here we are using the plasma accelerator.
That's correct.
Same Wakefield is generated.
Yes.
But in which case, I think that in the both cases, the Wakefield generation is had the same gradient or not?
No, in the dielectric accelerators, the one you're talking about, the dielectrics, you're actually limited by the breakdown of the material that you're actually going through. And so the breakdown voltages are probably something like 50 megavolts or something like that before you destroy the structure that you're using as the dielectric. That's the reason why conventional accelerators can only support something like 50 megavolts per meter. I don't think there's any accelerator that's greater than that. The copper component of the waveguide structure just begins to break down to produce the light.
Another question is that in the TNSA, target normal state acceleration, you make the nanostructure, more light is absorbed. Before the target, you make the nanostructure. It is possible to convert the more efficient ion acceleration. Suppose a target,
Yes.
and the incident side, if you use it in nanostructure, people are make the nano holes in the target.
Oh, yes. That's why they've gone to the light cell. You can make a small structure, a very, very thin target, and your foil would then be accelerated. So you're accelerating the whole structure through the light pressure. Yes, rather than having a lot of it absorbed at the front, and a lot of that energy is lost to the plasma. It's actually going to be blowing off the front side. That's correct. That's a very good question, and I didn't show this slide, but we can talk. I've got some papers on that and worked on that myself. What you find is that the ions that, if you're starting off with ions at relatively low velocity, then they're not moving at the speed of light. Electrons, it's very quick. They're very easily accelerated to high velocities. So the structures we're talking about are moving close to the speed of light. The ions are too rigid. They just wouldn't move. There are schemes that people have looked at which are based on modulating laser beams, which will produce a slow wave structure. Now, slow wave structures have been built in the laboratory to accelerate ions, but people are now thinking we could build a slow wave structure using intense lasers, and that's something that probably we could actually talk to you about, say, at one of the discussion sessions, where we're generating a slow wave structure that would accelerate an ion because it's going at velocities much less than the speed of light. And so you could actually do that. Now, if you're talking about accelerating, say, the TeV beam at CERN, then you find that the stiffness of that beam is so great. That's why the Wakefield, the self-modulated Wakefield experiment doing at CERN just now needs 10 meters of plasma, because it's very difficult to bunch together beams of 450 GeV. They're so stiff that it takes a lot of energy just to bunch them together. And so one of the problems that you've got once you've got to that energy is actually being able to keep them together. But once they're together in a wake structure, they might actually just blow apart. So these are things we can address. But I think one of the papers, there was a paper written about 2006 that looked at accelerating muons. And that was a muon beam coming out of a typical proton target interaction. And these muons are coming out with velocities less than the speed of light. And could you actually take them up to much higher energies? And so there was an idea of modulating laser beams, produce a slow wave structure, which is moving close to the velocity of the muons, and then have it chirped as well. So that slow wave structure is chirped, so that the accelerating part of the slow wave structure would actually be increasing in velocity. So these ideas are out there, but they're still in their infancy. No one's really done anything serious. No experiments, as far as I know, have been done at these energies yet.
More questions? Here's your opportunity.
Well, I'll be here all week, so don't worry.
Okay.
Yes?
How did the Landau damping, how did it enter into the idea of the...
Okay, I'll just do it in the blackboard. I mean, Landau damping is a process where you say, take a wave. If this is a kind of distribution function, f of v, and this is v, velocity, distribution of a bunch of particles. If the waves are here, right, then these waves will interact with particles here and pull them out and produce a high energy tail. So that was what Dawson was working on to prove that you could actually do. So you can actually act on particles that were going slightly slower than the wave and push them out to velocities that were high. As soon as you get to velocities higher on the wave, they start to give energy back as well. But if you've got a large spectrum, you end up with a plateau like that. But if it's a single spectrum, you end up just pushing those electrons along here. So that was the concept that he actually put forward in 61. But it took a long time. I mean, there was a lot of people, really scratching their head about it.
Time for coffee? Okay, so we break for coffee. Okay.